Alright, today we are going to take these general electrochemistry concepts we've been learning and transition to using them more analytically. But first, let's quickly recap two important concepts that we've seen recently. One, the Nernst equation, and two, the standard hydrogen electrode. For the Nernst equation, we learned how to determine what the true voltage of a cell is based on the actual concentrations, provided we're not at standard state. This equation is extremely important analytically because it gives us a way to relate something that we can measure, like voltage, to concentrations. Now, all of these standard state potentials that we can look up are measured with respect to the standard hydrogen electrode, this electrode we went over down here, where if we can put platinum solid with 1 bar of H2 gas and 1 molar of protons, we will have a half cell whose reduction potential will be 0, and thus the measurement that the voltmeter winds up reading can be completely attributed to the half cell of interest, since we know the voltmeter or potentiometer just measures the difference between the cell of interest on the positive wire and, in this case, the Xi on the negative wire, which has a value of 0. And so the Xi is what we call a reference electrode because we measure the voltage of some half cell of interest in reference to this electrode here, where we know its voltage. And on that note, let's just learn some new terms. We'll call this section reference electrodes. Reference electrodes. We use these to measure the voltage of some analyte we're studying for measuring E. For measuring E, particularly of an analyte. And so we'll learn two terms. One is going to be indicator electrode. Indicator electrode. And this is hooked up to the positive terminal. So its voltage is just going to be represented by E+. And what this is the electrode for the analyte. For analyte. So in the cell above, this would be referred to as the indicator electrode side. This is the voltage that we're trying to measure, and it is hooked up to the positive terminal. And then we have the reference electrode. Reference electrode. Which is hooked up to the negative terminal, as we see above. And this is an electrode where we know everything about it, because one of the common themes in analytical chemistry is to learn about something unknown, you must always compare to something that is known. And so this electrode must have a constant and known potential. Constant and known potential. Which we'll see momentarily means that the composition itself must be fixed. So fixed composition. And so the standard hydrogen electrode in principle is a very good reference electrode because we know its voltage, and that voltage is 0, which is easy to work with. But the issue is that it requires us remain at standard state while it's under operation. If it deviates from standard state, the Nernst equation tells us that the voltage will change. Now we will no longer know what its voltage is. We'll know that it's no longer 0 though, and that's an issue, because it can definitely be difficult to keep that pressure at a fixed 1 bar the entire time. Furthermore, the standard hydrogen electrode uses platinum, which is not exactly an abundant and inexpensive resource. And so typically we will use a reference electrode that's more convenient than the standard hydrogen electrode, and we call this the silver-silver chloride reference electrode. So let's write that down. Silver chloride reference electrode, ref electrode. And for now, we'll just say that it's more convenient than the Xi. more convenient than she. So first I'm going to show you what it is, and then we'll make some more notes about it. So here's the electrode. A silver piece of metal coated with some silver chloride solid paste, presumably, dipped into a solution that is saturated with KCl, and so that's what this mountain is, that's solid KCl. KCl is a strong electrolyte, but even a strong electrolyte can only dissolve so much before it reaches a saturation point where the solution can no longer handle any higher capacities of potassium or chloride ions. It's like we can imagine putting a teaspoon of salt into a glass of water and the salt would dissolve. But if we put in half a glass of salt into a glass of water, some of that's going to be left over because you've saturated the water solution. It can only handle so much dissolved salt. And when the solution is saturated like this, we have a different voltage than the standard state potential. So if you ever look up the associated half reaction for this electrode, and we actually have seen this in prior examples, you'll see two potentials, the one for standard state and the one for saturated KCl, which is actually the far more important value. Let's see why. What having a saturated solution does, like what's depicted over here, is it fixes our concentration, which in turn fixes the potential of the electrode. We'll get more into that momentarily. First, let's just go through a visual design to explain why our concentration is fixed over here and not over here with an unsaturated solution. So let's say we had this many potassium and chloride ions in solution, but then an extreme degree of evaporation occurs, causing the volume to go down by half. Well, this evaporation isn't going to change the objective amounts of K plus and Cl minus ions, and so they're going to be doubly concentrated as the volume they're swimming in decreases by half. It's basically like a dilution in reverse. So let's just see what I mean by this. There goes our volume, but look, our ions are the same as ever, but they're in a smaller volume, so they're doubly concentrated. Now let's direct our attention to a solution who is at maximum capacity for these ions, and thus any other KCl in solution has no choice but to remain in this solid form because it cannot dissolve any further. What do you think would happen if this water were to evaporate? You should pause and think about that because that's a good challenge question. Well, here's what would happen. If we had that same extreme degree of evaporation, causing the volume to decrease by 1/2, well, in principle, you'd think the concentration would increase like over here, but the problem is these concentrations are at maximum values, so they can't get any higher. So the only option for these ions is to precipitate out and form more KCl solid. And so here's what I'm describing. So the volume went down, increasing those ion concentrations, but the solution couldn't handle that. And so those K plus and Cl minuses just precipitated into solid, adding to that mound of KCl. And so the point of having that saturated solution in the first place is so that the concentration of ions will not change. Now let's establish why that's super important for our reference electrode. And so back to this cell over here, where that voltmeter is going to measure the voltage difference between the positive terminal electrode and the negative terminal electrode. What we just learned would be called the indicator and reference electrodes respectively. And we remind ourselves that both of those voltages are from the reduction point of view. But let's re-express the voltages in terms of the Nernst equation, since there's no guarantee that we're at standard state. In fact, that saturated KCl solution is definitely not at standard state. So for E on the plus side, we have the standard state voltage of that positive terminal electrode minus 0.05916 divided by N, but in this case we can see from the reactions that the N value is 1 for both sides. So above we'll just make the note n equals 1, and so we're not even going to bother writing it in the Nernst equation. So 0.05916 log of our product on the right side is Fe2 plus, concentration, no coefficient, so no exponent, and our reactant is Fe3 plus. Again, no exponent. And this expression represents that E plus above, and then we're just going to do the same thing but for the negative terminal side. So we'll have a minus symbol, and then in parentheses we'll write the Nernst equation, which is standard state potential of the negative terminal side minus 0.05916 log, and then the only thing that goes into Q is Cl minus. So let's analyze each of these terms we've written down. The standard state potential on the positive side is a constant number that we can look up. The concentrations of iron 2 plus and 3 plus, well, that's variable. That could be anything. The standard state potential over here is also a constant, which we can look up, and we can even find it on this slide. It is 0.222. And what about the chloride concentration? Is that constant or not? And the answer is it's a constant, provided we've saturated the solution for the reasons we went over in the previous slide. So in parentheses we'll write because KCl saturation. Because KCl sat. This is useful because it means that the only unknown or variable is the ratio of concentrations on the side that we are interested in studying. Thus, the voltage that the voltmeter spits out can entirely be related to this value here because we know all of the other values and we know that they are constant and unchanging. If our chloride ion wasn't set in stone, if we weren't saturated, then changes in the voltage here could be attributed to either changes in these concentrations or this one. But because this is a constant and not an unknown changing number, it means that the voltage we measure can completely be related to these concentrations and only those concentrations. That is why we wrote the note earlier that a reference electrode must have a constant potential, and that comes from a constant or fixed composition. And so this entire expression in parentheses is a constant value, and it's that 0.197 volts that we see in the table above. And this is hands down one of the most important concepts to understand in this entire unit, this need for a constant potential. So really make sure that this makes sense to you. If not, please ask questions. I'll animate in a couple of notes, so first let me erase this ink. This is pretty much just the summary of what we went over. If you had that reference electrode at 1 molar, i.e. standard state, you'd have that plus 0.222 volts, but it's not very useful since that chloride concentration may change over time, and thus so will the potential according to the Nernst equation. But when we saturate it, we fix it at a constant value, plus 0.197 volts, and that's super important. Now I'm going to quickly show you a couple of visuals just so you can see what this type of reference electrode looks like in real life. Because this image over here is designed to represent the reference electrode in a manner that you've seen so far in these simple beaker-based half cells. But in practice we use a more compact design. So in this case, instead of having this block of silver, we have this silver wire that's bent in this half loop. In between this loop is some silver chloride paste, as opposed to just putting paste on top of this solid slab. There's some solid KCl at the bottom, allowing us to have saturation in the solution, and finally there's this porous plug that operates like a salt bridge. So all of the components are there, but it's a lot simpler to use. So this is a more practical setup for measurements of that same cell that we were seeing in the previous slides. Except instead of having some unwieldy beaker setup on the left side, we just take this probe and stick it into the solution we're measuring, and there's our salt bridge connecting the two right there. And so that's just a much better setup to use.